Hi, in a previous video, I discussed how the index of refraction affects the speed of light as it goes through a medium. So briefly, what I'm going to do is just remind you of that. So imagine we go from a vacuum, here's a wave of light like that, and it enters into some medium that has a high index of refraction. What's going to happen is that the wavelength gets smaller, the velocity is reduced, but the frequency stays the same. So in this video, what I want to do is talk about what happens when light enters this interface between one medium and another medium at an angle. And when it enters at an angle, it's bent. And that's what we call the refraction of light. So I want to just describe the conceptual idea behind that, one way that you can think about it. And then that will lead us to another video after this that will talk about Snell's law, where I'll do a computational example. So I'm going to represent light as a wave like this, and wherever the wave has a crest, we'll have a vertical line like that, okay? So now what I want to do is take light, basically coming in at some incident angle, theta I, from this midline. This midline is our normal to the interface. The interface is right here between, on the left, a vacuum that has low index of refraction, and on the right, something that has a high index of refraction. So I'm going to draw the light wave in terms of these little lines like this. So these are the wave crests traveling along this arrow, right like this. And now when it gets to this material here, one of these wave crests is basically going to be in an interesting position. Let's take a look at this. This wave crest, conceptually, will be stuck in the high index of refraction, which means it's going to go slower, whereas this part of the wave crest is still in the vacuum, which is a low index of refraction, and it travels faster. So relatively speaking, this part is going to travel faster, and this part is going to act like it's stuck. And so things are going to pivot in a way like this. And remember, the wavelength changes also. When you go into a higher index of refraction, things are closer and closer together. So now it's going to look something like this. I'm exaggerating, and this is just a diagram, it's approximate. So it's going to look something like this. And if I were to draw a straight line that's perpendicular to these things, what you would see is something that looks like that. And what that means is that the refracted angle, theta r, is smaller than the incoming angle. So the incident angle, theta I, so the incident angle is greater than the refracted angle, theta r. And so another way of thinking about what's going on here is that when the light wave travels from a low index of refraction into a high index of refraction, it bends toward the normal line. It bends toward this dashed line in the middle. So basically it travels this way, and then it turns, and then it travels closer to the middle. When it goes into a higher index of refraction, it stays closer to the midline. So that's going from low index of refraction to high index of refraction. Let's take a look at the opposite case. So here's the opposite case. We've got a high index of refraction. Maybe this is diamond or something like that. We're going into a vacuum, okay? This is our incident angle like that. And again, what I'm going to do is draw the wave as a series of crests like this. And here the wavelength is relatively short because we're in a high index of refraction. Okay, so I'm coming like this. This is the wave propagating toward the interface. Now I'm going to draw it from this angle. And so now what we get right about here is this tip of the wavefront, in a way, is now in the vacuum, which is low index of refraction. So it can kind of travel faster, whereas this tip over here is still sort of stuck in the high index of refraction material where it's going more slowly. And so what that means is that these wave crests are now going to start to look like this. And remember, they're going to space out a little bit more because the wavelength is going to be longer in the low index of refraction. And what you should find, and I don't know if I've drawn it enough, but the basic idea is that it now bends outward like this, such that this angle, theta refraction, is bigger than theta incident. So theta incident here is less than theta refraction. It bends away from the normal, like that. And so what we know is that when it goes from a high index of refraction material into a low index of refraction, it bends away from the normal. So this is just a conceptual introduction to the consequences of what happens when you travel from one medium that has a particular index of refraction into another one, if you travel in a straight line, right, like that, it's not going to cause any bending. But if you travel at an angle, it will cause bending. And if you go from low to high, then you're going to bend toward the normal. And if you go from high index of refraction to low index of refraction, you're going to bend away from the normal. That's the conceptual roundup. In the next video, what I'll do is address this more computationally, talking about Snell's law, where we can calculate what those angles will be.